Okay, so I'm happy to introduce now Luis Medina from University of Puerto Rico, and he will enlighten us about the Walsh-Hadamard transform of this long title. Please, you start and you explain to us all these words.
Okay, I want to start by thanking the organizers for the invitation. And my name is Luis Medina, and I'm from the University of Puerto Rico. And today I'm going to talk to you about Walsh-Hadamard transforms of generalized p-ary functions and C-finite sequences. This is a joint work with my former PhD students, Leonid Sepulveda and Cesar Serna Rapello. It is a short outline of my talk. It's very simple. I will start with some basic definitions. After that, I will move to some known results in the area. And finally, I will show you the results that we have. I will start with a definition that probably most of you know. A sequence AN is called C-finite if it satisfies a homogeneous mean recurrence with constant coefficients, that is, if it satisfies a recurrence of this type. So here, we require the coefficients to be constant. Of course, there are classical sequences like the Fibonacci sequence that is a C-finite sequence. In fact, most of the time is defined by this recurrence. And there are other sequences like the factorial sequence, which satisfies a recurrence, but it's not C-finite. In this case, it's holonomic, but not C-finite.
Sorry, we're missing the bottom of your slides.
Yes.
Oh, you cannot see them? Oh,
No.
so let me do the following.
We only see about 80%.
80%.
Now we can see.
Okay, so I will do it like this then.
In a continuous way, yes.
Okay, good. So I was telling you that the Fibonacci sequence is a classical example of a C-finite sequence. In fact, most of the time it's defined by this recurrence. And the factorial sequence is an example of a sequence that satisfies a recurrence, but it's not C-finite. In this case, is holonomic. The main objects that I will work with are p-ary functions. So let P be a prime. I will let FQ represent the finite field of Q elements. A function from FQN to FQ is called an invariable p-ary function. So most of the objects that I will work with are these type of functions, and the set of all these functions will be denoted by B and Q. Most of the applications of p-ary functions, you can see this, right? You can see the bottom part? Yes. Yeah. Most of the applications of p-ary functions occur when Q is equal to 2. This is expected. Most of these applications can be found in cryptography, coding theory, information theory. In that particular case, when Q is equal to 2, we call these functions Boolean functions. Even though these functions have a lot of applications, in this talk, I'm not covering them. So I just let you know that they do have applications. It is an important fact in the area that every p-ary function can be identified with a multivariable polynomial. This multivariable polynomial is the algebraic number form of the p-ary function. So that means that basically, when you're working with p-ary functions, you're working with this type of polynomials. Okay. In some applications related to cryptography, especially in the case when Q is equal to 2, it is important for these functions to be balanced. Okay. So what is the definition of balancedness? We say that a p-ary function is balanced if its values are uniformly distributed. That is, if f takes each value of fq exactly qn to the minus 1 times. Okay. Let's do a toy example here. Let's consider the following function, the following linear function. So we have x1 plus x2, and we will consider that function over f3. Okay. Now here you can see the output table of the function. And as you can see, you have 3 zeros, 3 ones, and 3 twos. So this is an example of a balanced function. Okay, now another object that I will work with in this talk, in this work, are the transformations that are known as Walsh transformations. So the Walsh transform at a point A of an n variable p-ary function f is the following complex valued function. Okay. Here, TR just represent the field trace function that goes from FQ to FP, and A dot X represent the regular dot product on F Q to the N. Walsh transform, especially in the binary case, in calculation of important cryptography properties, for example, like nonlinearity and the property of being a bend function. Bend functions are basically the functions that are farther away from linear functions. And again, I'm just telling you that they have this property, but again, we are not working on this type of application, so I'm just letting you know that they have those applications. Okay. Now, in the particular case, when A is equal to the vector 0, the Walsh transformation gets reduced to this sum. This particular sum is known as the exponential sum of the p-ary function. Exponential sums are very important in applications because they can be used, among other things, to detect when a particular function is balanced. And if you remember, balance then means that the values of the function are uniformly distributed. In particular, if the p-ary function that you're working with happens to be balanced, then the output of the exponential sum is 0. So let's do the following example. So we just take a random, we just put random numbers here from 0 to 2. And the theory said that this function, this p-ary function, should be a polynomial, and that is the case. In this case, the polynomial representation for this function is this. The arithmetic will be main mod 3. And if you want to calculate the exponential sum, then it would be given by this. In this case, for example, let's suppose that I don't know the function. By just seeing the exponential sum, I can actually say that the function is not balanced. It's not balanced because this expression is not 0. If you want it to be 0, you need this one to be a 2, or maybe all of this to be 3. But that is not the case. So I know that the function is not balanced. Also, the exponential sum gives me other information, because without knowing the function, I already know that in the output table, there are 2 zeros, 5 ones, and 2 twos. Okay. Now, when you're working with Walsh transformations and exponential sums, one of the issues that you encounter is that their calculations, if you want to make them using the regular definition, is computation expensive, right? Because they exhibit a growth, an exponential growth in the number of variables. So what mathematicians and scientists do in this area is that they impose conditions on the underlying function with the hope that the calculation of the Walsh transformation or the exponential sum get easier. I present you here one of the families that I work with. A p-ary function is said to be symmetric if it doesn't matter how you permute the the arguments of the function, the value of the function stay the same. Another way to say this is that the p-ary function is fixed under the action of the symmetric group of n symbols. Now, when you're working with symmetric functions, then it is normal for you to see elementary symmetric polynomials. So this elementary symmetric polynomial in n variables of degree k would be denoted by E and K in this work. For example, if you see E for 3, that means that that we're talking about the elementary symmetric polynomial in 4 variables of degree 3. So we're talking about this expression here. Now, some known results in the area. Exponential sums over FQ, so we're talking exponential sum over finite fields, of elementary symmetric polynomials are C-finite sequences. This means that you take your elementary symmetric polynomial and you fix the degree. Let's suppose that you want to work with, let's say, en5. So you will fix the degree and you will let the number of variables grow. Then you will get, and you apply the exponential sum to it, then you will get a sequence. And that sequence is actually C-finite. This is known since the 90s for the Boolean case. And the general case was proven in 2018. Exponential sums of rotation symmetric Boolean functions are also C-finite sequences. This was done in 2017. A rotation symmetric Boolean function or rotation symmetric in general, doesn't have to be Boolean, can be in other finite fields, are functions that are fixed under the action, not of the symmetric group, but the action of the cyclic group of n symbols. So if the function is fixed under the action of the cyclic group of n symbols, then we call it rotation symmetric polynomial function. And if it's fixed under the action of the symmetric group, then we call it symmetric function. These functions have a lot of applications in cryptography. Then later in 2018, it is shown that Walsh transformation. So the first two results are for exponential sums, but the third one is for Walsh transformations in general of symmetric and rotation symmetric Boolean functions are C-finite sequences. That was proven in 2018. And then finally, also in 2018, it is shown that exponential sums over FQ of rotation symmetric polynomials are also C-finite sequences. So this means that all of these sequences, either exponential sum of elementary symmetric polynomials or of rotation symmetric polynomials, are known to be C-finite. So that means that they can be calculated quite fast. So here is an example. Let's suppose that we are interested in calculating the exponential sum of en7. This is the elementary symmetric polynomial in n variables of the degree 7. Then the first few values are given by this sequence. We know that this sequence is C-finite. In fact, it satisfies the following recurrence. This implies that the characteristic polynomial is given by this, and this one can be factored as this. So in this factorization, you can see shifted cyclotomic polynomials, and this is true in general. And by general, I mean when you're working with symmetric functions and you calculate exponential sums of them, the exponential sum satisfies recurrences, and the characteristic polynomials are made by multiplying cyclotomic polynomials, and the indexes here are power of 2s. And of course, for example, just if you want to calculate E157, that will give you a value that is close to 20,000, and you use the regular definition. At least on my computer, it took 4 minutes to calculate it. But of course, if you implement the recurrence, then as expected, you can do it in an instant. So this is one of the reasons why people in this area are trying to show that certain families of functions satisfies recurrences, because then you can make calculations quite fast. Okay, now I will present some of the results that we have in this area. Now, before giving this definition, I will give you why we are studying this. Most of the applications, as I told you, starting in the Boolean case. Like most of the application in cryptography, coding theory, information theory were done there in the Boolean case. Then these results were extended to FP and FQ, to the finite case. And now the experts in the area are working with generalizations of Boolean functions and generalization of p-ary and p-ary functions. And what we're trying to do is try to see if many of these results can be extended to these new families of function. A function from fp to the n to zm. So here, if you remember the definition that we have before, here instead of having zm, we used to have fp. But if a function goes from fp to the n to zm, that is called a generalized function in this case, and the set of all generalized p-ary functions will be denoted by this symbol. If m happens to be a power of p, that is, if m is p to the l, then every function that is a generalized p-ary function can be expressed as this, where in here the components that you see, the AJs, happens to be regular p-ary functions. Of course, we were working with exponential sums and Walsh transformations in the general case, so we have to extend those transformations to this case, and in this case, the generalized Walsh transform at a point A of a generalized p-ary function is given by this expression. Okay. Now we introduce a notation. Let's suppose that you're working with a list like this. Let's suppose that it's fixed in some sense. Then this list would be denoted by this. So you see KT square bracket, that means that we're talking about a sequence like this. Okay, so the index T here tells you how many of them are. Now, with that definition, or with that notation, if you encounter a sum like this one, then we will simplify the notation a bit and write this. So this is not a singular sum. This is not a single sum. In fact, it's a multiple sum like this. Also, if for some reason you need to split the indexes of the A that you have here, or the sequence that you have here, let's suppose you want to, for some reason, split them in some Ks and some Js, then this multiple sum can be expressed as this. And again, when you see this, this is actually a multiple sum, not a single one. Okay. So the first result that we had is that generalized Walsh transform of generalized p-ary function of the following type. So these are the type in which the m, the zm that you have, the m is actually a power of p. If that is the case, you know that every p-ary function can be written in this way. And once you write it in that way, then the generalized Walsh transform happens to be a linear combination of regular Walsh transforms of linear combination of the p-ary functions that appear here, the components. So basically, this result is telling me that when you're working with generalized transform, generalized Walsh transformations, you can actually express them in terms of regular Walsh transformations. The proof is not that hard. Just have to keep track of the algebraic manipulations that you're doing. And once you do that, you can express the generalized transform of the generalized p-ary function as this expression. Again, remember, this is actually a multiple sum. Here, the G that you see here is this expression. The B's are the components of the p-ary function. And the C here are some constants that are given by this expression. So it's not hard, it's just tedious. You have to keep track of the manipulation, but this is good. Now, the second result that we got is the following. If P happens to be a prime, so right, let's suppose that you have a generalized p-ary function and you write it like that, but the components that you have are either symmetric, rotation symmetric, or a combination or concatenation of them. Let's suppose that A is fixed in some sense, then this sequence that you have here, so this is the sequence of generalized Walsh transformations, happens to be C-finite. In the particular case, when the components of the function happens to be symmetric. So remember, this is true in general. By general, I means if it's symmetric, rotation symmetric, a combination or concatenation of them. But if this just happens to be symmetric, then we know that they are C-finite sequences, but also we're able to calculate the characteristic polynomial of a sequence of a recurrence that it satisfies. And in this case, the recurrence will be this one. So basically, the characteristic polynomial of the recurrence will be this one. Here, D is given by this expression. Okay. Now, the next result that we have is a result that we're using in order to study the asymptotics. We know that if they are C-finite sequences, then you basically can express them in terms of the roots of the polynomials. So in this result, what we're doing is we're studying how big can be those roots. And with that information, we can say things about being balanced or being properties like band function. So let's suppose that P is a prime, and let's consider the cyclotomic extension given by this. Let's suppose now that you have a family. These are not generalized p-ary functions. These are just regular p-ary functions. Let's suppose that is a family, and you know that the Walsh transformation satisfies a recurrence with integral coefficients. So let's suppose that you know that. Let's suppose that Q happens to be the characteristic polynomial of the minimal of such recurrences. And let's suppose also that it happens to be a square free. So it has a square free irreducible factorization. Then every root of the polynomial is bounded by P modulus. So the absolute value of all the roots is less or equal than P. Moreover, if each of the Qj happens to be x and the degree is bigger than 1, then we have equality here, only if there is a j for which this expression is palindromic and of even degree, have to be of even degree. So we'll finish with 2 examples. Let's consider the following sequence. Here A is equal to this. Then this sequence satisfies the following, the recurrence whose characteristic polynomial is given by this. The first theorem said that this recurrence should satisfy this polynomial, and it does so because this is actually a proper factor of this. And if you calculate the roots of it, the maximum modulo occur here, and this is less than 5 as the theorem predicted. It is an example of a function. I know that my time is off, but let me finish with this. This is an example of a rotation symmetric polynomial. So in this case, you start with x1, x2, x3. You add 1 to the indices and you go to here. You add 1 to the indices and you continue doing this until you get here. Then you add 1 again. This one will move to n minus 1. N minus 1 will move to n, and n will move to n plus 1. But n plus 1 is not one of the variables. So what we do is we mod n, and you get 1 here. So this is why we're calling a rotation. And you do the same here, you get this factor, and then you finish here. Then this sequence, when a is equal to 0, satisfies a recurrence, and the characteristic polynomial of such recurrence is this one. And again, the highest root here has modulo the third root of 3, and that is clearly less or equal than 3. So my work was supported by the Puerto Rico Science Technology and Research Trust. And you can find this work in this address. As of today, no, there is a blackout at the university, so the server is down, but eventually you can find it there. Thank you.
Thank you. So good. Do you have any questions for Luis? So you mentioned that I agree with you that these n-ary functions or Boolean functions have many applications.
Yes.
What be the application? Is there any direct application of this Walsh that these operators that you're considering? How do they show up, or why did you think of them?
Yes. I don't do the application per se, but what they do is, for example, for the Walsh transformation, that transformation can be used to calculate nonlinearity of the function. The nonlinearity is very important because you don't want, when you're doing applications with Boolean functions, you don't want them to be easily approximated by linear functions, because then it can be break. So what you do is you use the Walsh transformation to calculate the nonlinearity, and the higher the nonlinearity, the better.
Interesting.
So the Walsh transformation can be used to do that. And the exponential sum can be used to detect when the function is balanced or not balanced. But again, I don't do the applications per se, but
No,
this
no, that's
is,
okay, but I was asking for the motivation of this
yeah,
definition.
that's the motivation. In fact, one of my colleagues, Pantelimon Stanica, works directly on those applications, and that's
Mhm.
what he does. But I don't do that. I like the more the theoretical part of it.
Can I ask for
Please.
these proofs for that these things are C-finite? Do you have an order, and then with the order you can compute the recurrence or a bound for the order or something?
Yes, in fact, for symmetric polynomials is quite easy. The order is 2 to the r. R is depend of k being the degree. And in fact, we have an explicit one. So it's basically it's a multiplication, it's a product of cyclotomic polynomials. For rotation symmetric, we do have a guess, but I don't have the bound for it. We just know that they are C-finite sequences. We can embed this problem into a matrix, and then we calculate well, I guess you can use actually the order of the matrix, but the order of the matrix is something that we don't necessarily know a priori. But you can actually embed the whole problem into a matrix and then calculate an annihilator of the matrix, and that annihilator will be a characteristic polynomial for the sequence. That means that you can actually, using that annihilator, you can actually construct a recurrence.
Thank you.
Good. So I have to stop you here because we
Yeah.
need to move to the next lecture. Thank you very much.